In section 10.2, we are going to continue with control charts for variables. So the learning goals of these sections are to review the definitions of R chart, S chart, and control limits. But we are going to concentrate in defining the X chart, and the X chart could be built based on the R or in the S chart. So we are going to compute the control limits for the X chart. Next video, we are going to calculate the ARL, the average run length. Now let's review some of the concepts that we covered in the last video. First of all, the variability of the production comes from two different causes. One is the common causes, and the second one is the special causes. So if the process is in control, means that only common causes are present in the production. And we said that the process is out of control if there are special causes. We use the chart to identify if there is any special cause that needs to be addressed. Remember that the variables are binary, count, or continuous, but in this couple of videos we are concentrated just in the continuous variables. Now, for variable data, we have two steps. So we define the R chart or the S chart and measure and control the variability of the process by computing the upper and lower limit. And then in a second step, we have the X chart that is used to control the process mean. Remember that the most important assumption here is that the measurements follow an approximately normal distribution. Let's review for a moment how we collect the data. And remember that we have a time during the process is running, and then we divide that time in some sampling times, so which are equally distributed over the whole time the process is running. And at each sampling time, we do a sample. The sample could be analyzing the units around that sampling time, or can be equally distributed in between sampling times. So each sample is called a rational subgroup, and we need to have more than 20 of those samples, and each sample consists of the analysis of 3 to 5 units. So in the example that we were, 3 to 8 units. So in the example that we have, this was the data, and so we have 32 samples. For each sample we compute the mean, the range, and the standard deviation, and then we compute the mean of the samples. So X double bar, we compute the mean of the range, and we compute the mean of the standard deviation. Now, the process is two steps. First, we have the R chart to assess the variation in the sample range, and then we have the X chart to assess whether the process mean is in control. So for the R chart, we use the table that contains the constants. So the constants are going to approximate the upper control limit, and remember that upper control limit is the mean plus 3 times sigma, and the mean of R is just R bar plus 3 sigma, and the whole number R bar plus 3 sigma is approximated with the constant D4 multiplied by the mean. In the same way, the lower control limit, which is the mean minus 3 times sigma, is approximated with the 3 multiplied by R bar. Now, for the X chart, we can compute the upper control limit and the lower control limit in a similar way using different constants in the table. So the first upper control limit is mu x plus 3 sigma, and mu of x bar is approximated with x double bar, but the whole number is approximated with x double bar plus a2 multiplied by r bar. The lower control limit, which is the mean of x bar minus 3 times sigma, is approximated with x double bar minus 3 sigma x, and 3 sigma x is approximated with minus a2 multiplied by r bar. So we find the a2 value in the table. Let's have a look to table 18, which contains the constants to build the control charts. So these constants are a function of n, and n is the sample size. In the example that we are presenting, our sample size is equal to 5. Now, to build the R chart, we use constants d3 and d4, and to build in the S chart, we use constants b3 and b4. Now, depending if we are testing variability with the S chart or the R chart, the second step is to build the X chart. So if we use initially the R chart, then we should use the A2 constant. But if we are testing variability with the S chart, then the mean should be tested with the A3 constant. Okay, let's have an example of how to determine the X chart. And in this case, we are going to determine the X chart using art. So first of all, we have to guarantee that the variation is in control. And now we need to assess that the process mean is in control by plotting the X chart. So we determine the mean of the mean, so x double bar, so that's our central point, and the upper control limit and the lower control limit are given by the A2 constant. So we have x double bar plus A2 r mean for the upper limit and negative for the lower limit. Remember that the samples are drawn from a normal population with mean mu of x bar that is equal to mu, so the mean of the population, and the standard deviation of the mean of the sample is sigma divided by the square root of n. But in general, these values are not given, and we are computing those values from the sampling that we are doing. So we have to estimate the means. So the mean of x is given by the mean of the sample means, and the 3 sigma x is approximated with A2 multiplied by R mean. So remember, A2 depends on the sample size. Let's compute the X chart limit as a function of the range. And we are going to use the data from example 10.2. Now, remember that to start the X chart, we need to be sure that all of points out of control are removed. So in our particular case, we have to remove 0.6. Now, after that, we have to recompute X double bar and R bar, so the mean of the means and the mean of the ranges. Now, the upper control limit is equal to mu plus 3 sigma and is approximated as X double bar plus A2 multiplied by R bar. Now, the new mean is 2.658 plus A2. So A2, if you remember from the table, A2, because it's based on the range, is 0.577. 0.577 multiplied by the mean of the ranges, 0.5836, and the result is 2.995. Now, the lower control limit is mu minus 3 sigma, which is approximated with x double bar minus a2 multiplied by r. So the main difference is the negative sign, and the value is 2.321. As we plot all the means for the different samples, we can notice that there is a range of points that are outside of the upper control limit. So therefore, these points are out of control and they need to be addressed. Okay, some comments about that. When there is an out of control signal, the process must be stopped and the special cause must be fixed. And fixed doesn't mean just remove the points from the table. You have to look for the causes. So even when the process is in control, the process must be continually monitored, since new special causes are bound to crop up from time to time and will need to be detected and corrected. Note that while control chart can detect the presence of a special cause, they cannot determine its nature, nor how to correct it. So that's up to the engineer that need to have a good understanding of the process. So when the special cause is detected, he needs to actually go to the process and correct it. Okay, these are the summary of steps for the control chart. And these are for building the R chart and the X chart. So first of all, we choose the rational subgroups. We compute the means and the range and the standard deviation for each sample. Then we need to compute the R chart. And to compute the R chart means we compute the mean, the lower control limit, and the upper control limit. And then when we plot, we need to determine if there are special causes for any out of control point. And we need to delete the out of control samples and recompute. Remember, this delete means that we had addressed the problem in real life. And then after we fix it, we have to compute the new X bar, the new R, and the new S. Once the R chart indicates that we are in a state of control, we need to compute the X chart. So if the X chart indicates that the process is not in control, we need to identify and correct any special causes. Again, it's not just deleting the point, so we need to go and fix the actual physical problem. And then we have to continue to monitor X and R. Okay, all these steps can be automatically made with a script in Python that I will include in the notes. Now, up to this point, we compute the R chart and then the X chart. The second option is to compute the S chart instead of the R chart. And in general is the best method for variability. So in an S chart, the center line and the 3 sigma upper and lower limit control limits are given by the B4 constant. So the B4 constant. So the center line is S bar, the mean of the standard deviation, and the upper and lower control limits are given by the constants B3 and B4. B3 and B4 are in the table. So we don't use this for the S chart, we use this, which depends on the number of sample sizes. So for the S chart, we proceed in the same way. So the only difference is that the constant is different. We use the before constant. And in the same way, after we plot the central S bar and the upper and the lower control limits, we need to identify the points that are out of control. Now, once we fix the points that are out of control, we need to compute X, but now X is based on S, not in R. So for X, the upper control limit is X double bar plus A3S, and the lower control limit is X double bar minus A3S bar. And A3 is found in the table. So we compute the S chart once we remove the points that were out of control, and then we have the X chart. So the X chart with the limits given by these expressions. And we look if the points are out of control. So in the previous example, remember, n is equal to 5, and then we look for A3, and A3, okay, n is equal to 5, A3, which is for X based on standard deviation, is 1.427. 1.427, and so we can compute the limits. So this is the value corresponding to the upper control limit. For the lower control limit is just the same but with a negative, so this is the value resulting from this calculation. So which one is better to use, R or S? Well, both are going to give some similar results. So the range is estimating the standard deviation. So what is more precise? Well, I would say that S, because it's a better estimation of the process variability, and the range is just an approximation of S. It's probably easier to calculate, but with computers in this day, there is no need to do any simplification. It's same as fast to compute one or the other. So using S has less uncertainty, and therefore for that reason is preferred in many occasions. I think the range is has more historical background than any other thing. So remember that there is a close connection between the control chart and the hypothesis test. So the null hypothesis is that the process is in a state of control. So the null hypothesis is that mu is equal to X double bar, and a point that is plotting outside of the 3 sigma control limits present evidence against the null hypothesis. And remember that the 3 sigma limits is equivalent to the 99.9% of the range. So if it's outside of the range, it's just very far away. Okay, occasionally a point will plot outside of the control limits when the process is in control. So this is called a false alarm. If no point plots outside of the control limits and the process is not in control, so the opposite case, then we say that we have a failure to detect. So it is desirable for these errors to occur as infrequently as possible. The frequency which these errors occurs is called the ARL, average run length, that we will cover in the next video.